Welcome back to Linear Algebra for Economists. In this presentation, we will be moving on with matrices and matrix operations. In the last video, we saw that calculating how much Alice has to pay at the grocery store can be calculated as the dot product of the quantity vector, which contains how much she bought of each item, and the price vector, which contains how much each item costs, which we of course already knew how to do. Then we pose the question, what would happen if she perhaps has multiple shopping lists or there are several different supermarket options. In other words, when we have lists of lists, which we will be calling matrices at this point. Matrices, for the purposes of economics, are ordered rectangular arrays of numbers, and we specify their shape as row and column, so an n times k matrix, n by k matrix, means that it has n rows and k columns. So for example, here we have two matrices. On the left hand side we have a 2 by 4 matrix, which is 2 because it has 2 rows and 4 because it has 4 columns. And on the right hand side we have a 3 by 3 matrix. We either put them in square brackets or round brackets. Examples of matrices include the 2 by 2 identity matrix, which we can see here. It has elements 1, 0, 0, 1. Similar object is the 5 by 5 identity matrix, where on the so-called main diagonal we have all ones, and everywhere else we have zeros. For the third example, we have the 3 by 2 ones matrix, which means that it's a 3 by 2, 3 rows and 2 columns matrix, all populated by ones. Finally, we have some general matrix. This one is a 2 by 3 matrix with some general entries such as -2, 0.11 pi, the cosine of 43.5 degrees, and so on. So basically we can have whatever numbers in matrices. Just as with vectors, we also like to define matrices using formulas for their general entry. The first index, usually I, refers to the row, and the second index, usually j, refers to the second index, or the column index. One example could be that we can define the 2 by 2 identity matrix, which we just saw earlier using our Kronecker delta. So Ij would be delta Ij, which means that the first row, first column is delta 1, 1, the first row, second column is delta 1, 2, and so on and so forth. And we remember from the definition of the Kronecker delta that this will lead us to this 2 by 2 matrix. For our next example, we have Aij equaling I plus j. So here we can see that this will lead to this 2 by 3 matrix. The top left element we have 1 plus 1, in the middle top element we have 1 plus 2, and so on and so forth. For our next example, we have that Bij should be -1 to the I plus j, and this will leave us with a bunch of powers of -1. And as you remember, if the exponent of -1 is a odd integer, then we will have -1 as a result. And if it's an even integer, then we will have +1 here. So this will leave us with this array of +1s and -1s. This -1 to the I plus j will come up later. For our next example, we have a 4 by 2 matrix denoted by C, where C is defined as Cij equals I to the j, which leads to C being equal to the following matrix. So I, which is the row index, will be the base. So in the first row we have 1 for our base, in the second row we have 2 for our base, and so on. And j, which is the column index, is the exponent, which will lead which results in having 1 in the exponent in the first column and 2 in the exponent for the second column. And for our final example, we have a 2 by 5 matrix for which dij is 3. So notice that it doesn't depend on I or j. So this will be a constant 3 matrix. Every single element is 3. So this can be easily expressed with the all ones matrix. A concept that is sometimes useful is the transpose of a matrix. When we take the transpose of a matrix, that means that we flip it about its main diagonal. This is used when we want to reorient our data in this way. Now let's return to Alice, who now has to manage 3 weeks of shopping. For each week we have different amounts of bread, milk, cold cuts and beer to buy. And moreover, she has 5 supermarkets in her area that she could choose from with different prices for each of these products. Our goal here is to put together a table that contains the possible sums week by week for each supermarket. That is, this red-blue table. So if we have red here for the rows and orange here for the columns, and in the second table we have orange for the rows and blue for the columns, then we are interested in putting together a red-blue. So for each week shop pair, the cost for shopping for week I in shop j can be calculated as the dot product of these respective vectors, so just like before. And the resulting sums may be collected in a new table. So if we do this for all of these shop week pairs, we will get the following table. So as a result, we got a new table which we'll call the product of these two matrices. So basically we took a 3 by 4 matrix A containing the week by week shopping lists and multiplied it together with the 4 by 5 matrix B. Notice that this 4 was common in the two matrices because it represented the number of items that we were interested in. And the formula for the results was that in C we got the IK index element by adding together the appropriate products of AIJ and BJK, where J is a summation index. And we have to do this for all I and all K indices. One way to remember this scheme is through the following figure. So just to reiterate, we multiply the 3 by 4 matrix together with a 4 by 5 matrix, and we got out a 3 by 5 matrix as a result. So this is the criterion for matrix multiplication. These middle dimensions must agree, and the resulting product will have these outer dimensions. This criterion implies that not any two matrices can be multiplied together, so unlike with numbers, for some matrices it might happen that A times B exists, but B times A does not. And even if both A times B and B times A exist, they still might be different shapes. And even if both A times B and B times A exist, and they are of the same shape, they might still be different. Let's take a look at a couple of examples. So here we have the matrix 1, 2, 3, 4 multiplied together with the 2 by 2 matrix 5, 6, 7, 8, so not very creative. So if we remember our scheme, we can put this together. So using the previous scheme, we have that we need to multiply 1 with 5 and then add 2 times 7, which is 14. Here in this element we have 6 plus 16. In the bottom left corner we have 15 plus 28. And finally here we have 18 plus 42. And if we crunch the numbers, we get the matrix 19, 22, 43, and 50. Multiplying the two same matrices in the other order together will give us 23, 34, 31, and 46. Notice that this is a different matrix from the previous one. Similarly, it's a good exercise to calculate that this product would be equal to this, and this product would be equal to this. So just set up the appropriate scheme and multiply these together. Again, notice that these are the two same matrices multiplied together, and they are of different shapes. And the products are of different shapes. Final two examples is yet again the two same matrices multiplied together. In one scenario we get a well-defined answer, and in the next scenario we have an undefined product. In the next video we will introduce determinants of matrices and then later see how matrices and their determinants can be used to solve systems of linear equations. See you in the next one.